So this in pure capacitive circuits, these synchronous condensers and the capacitive banks acts as the power factor improvement. Okay, so first of all, you should know what the power factor is. So I will briefly discuss about this. So if the current is lagging the voltage by any angle phi, or you can say it is leading by any angle phi 1. Okay, so whatever it may be, so the cause of the angle between the current and the voltage is called the power factor. Okay, so in the inductive case, pure inductive case, we have just seen that the current phasor was at 90 degrees lagging position to the voltage phasor. Okay, but in the capacitive circuit, it is inverse. Here, the current phasor is leading the voltage phasor by 90 degrees. Okay, and in between circuits, which can be RL circuit, RC circuit, so the angle, this phi angle, this circuit, so angle will be lagging, current will be lagging, but not by 90 degrees. It will be lagging by, say, any angle phi. So the power factor will be cos phi. Okay, and in RC circuit, since the current is leading but not by 90 degrees, so phi is there, so cos phi is again power factor. So sometimes we since x-axis is taken as reference axis, so the RL in RL circuit, the current which is lagging can be denoted by minus phi. Okay, so in that case minus phi is here, but cos of minus theta is equal to cos theta, so it does not affect the power factor equation. Okay, so the average power of the single phase circuit is Vi cos phi. Okay, so applied voltage is constant, which is the RMS value, so it is taken as constant. Okay, so and the RMS value is also written on the load which it can sustain. So if the power rating is also mentioned on the load, suppose it is 40 watt tube light or 1500 watt immersion rod or electric geyser, electric kettle, etc. So the power remains same, voltage remains same. So there is a relationship between the current and the power factor. Okay, so if the power factor is less, government has allowed the power factor to be 0.8. The power factor is always less than 1. Okay, and if the inductive load is there, the power factor decreases, and in the industries, induction motors and inductive load is more, so the power factor reduces. Okay, So the power factor reduces 0.8 is the acceptable limit, and if it decreases beyond that, okay, it means that that loss of power is to be compensated by the current. So more current will be drawn from the mains. Okay, so when more current is drawn for the same power consumption, it is a loss to the nation. So country applies penalties on less power factor. So how it can be improved? Inductive load can be compensated by the capacitive load. So these capacitive loads in industries are mainly the capacitive banks or the synchronous condensers or capacitive capacitors which we use. Okay, so this is brief about the capacitive banks. So these are the industrial applications of the pure in capacitive load. Okay, in our household applications, it does not have many applications. uh, Even if we talk worldwide, the worldwide if we talk again, the component of the capacitive load is very less. It is hardly 5 to 15%. Okay, the rest are all either resistive load or inductive load. Okay, so the load which can be applied in the household circuits is the piezo buzzer or the piezo motors. So buzzer, buzzer which is connected at our main gate of the home, or it can be used for quizzes, etc. That is a normal buzzer, but if it is based on the piezoelectric crystal principle, so it is called piezo buzzer. So what is this piezoelectric principle? If any crystal is applied force, mechanical force or pressure, some deformation takes place in that crystal. Okay, so if some deformation takes place in that crystal, electrical signals are produced. Okay, so that contributes to the piezo buzzer and the piezo motors, etc. Okay, so this is the circuit of the circuit diagram of the pure capacitive circuit, pure capacitive load, where instantaneous current is there, instantaneous voltage is there, and capacitive load is there. This is the phasor diagram which I have just explained. So current is leading the voltage by 90 degrees, and the capacitive reactance is Xc, and it is denoted by 1 upon omega c. Okay, so if we want to express as Ohm's law, so it will be like this, and when Xc is replaced here, so it becomes 1 upon omega c. So 1 upon omega c is there. So this you can say is the Ohm's law representation of the current, which is shown here in the phasor diagram. Okay. So now let us focus on the waveform. So this is the waveform. Here again we firstly draw the voltage waveform or the cos wave. then is the current. Now we have just seen that the current is leading the voltage waveform by 90 degrees. Okay, so what does that mean? Since we have taken the reference axis as x-axis, okay, so it means that the zero crossing of the cosine wave will be 90 degrees ahead of that of the cosine sine wave. Okay, so this is our current. So it has crossed the zero axis or the reference axis or the x-axis 90 degrees before that of the voltage waveform. Okay, so we can understand that the current is leading the voltage by 90 degrees. Okay, so the equation of the current will be omega t plus pi by 2. Okay, pi by 2, 90 degrees, all the same. So once we get, similarly, uh, since the current is beginning pi by 2 ahead, so it will also terminate pi by 2 ahead. Okay, so now we will talk about the instantaneous power, which is Vi. So we will just multiply these two equations of voltage and current. So P is Vi. So V is Vm sin omega t, and I is Im sin omega t plus pi by 2. Okay. So sin 90 plus theta is cos theta. Okay. So we can replace this 90 plus omega t by cos omega t. Okay. It is also evident from the waveform because this is our cos waveform, cosine waveform. Okay. So now it becomes the formula. We can multiply by 2 and divide by 2. Okay. So now it becomes 2 Vm Im by 2. We have multiplied by 2 and divide by 2. And here we have get where what we have sine omega t and cos omega t. So this 2 will be used here and it becomes 2 sine omega t cos omega t, and 2 sine theta cos theta, it becomes 2 sine 2 omega t. Okay, so now you can remove this. So this is the situation now. Vm Im by 2 and sine 2 omega t. So now again we can see that the frequency of the instantaneous power is twice that of sine wave or the cos wave. Okay, so it will terminate or complete its first half cycle when there is passage of pi radians. Okay, so and here we are not talking about the magnitude, although say Vm is having the magnitude of 2 and Im is having the magnitude of say 3. So magnitude of the instantaneous power will become 3 into 2 by 2. Okay, so this is the peak value. It is achieved when the angle is pi by 4. Okay, as I have just mentioned that uh, it will have the value at every point, but at the angle which is half of that the cosine wave. Okay, so it will have zero value in pi by 2, negative peak at 3 pi by 4, and so on. Okay, so this waveform is clear to you now. Now let us understand the equation of this pure capacitive circuit. So as the inductive load deals with the storing of energy, or you can say that the inductor energizes and de-energizes itself depending upon the situation. Similarly, this capacitive load or the capacitor charges and discharges itself depending upon the polarity of the applied voltage. Okay, so let us see what is happening in the polarity. Or during the first quarter cycle, the applied voltage increases to its peak value and capacitor is charged to that value. Okay, so why capacitor is charged to that value? Because we know the formula of charging or discharging. Q is directly proportional to V. So during the first half cycle, it charges itself and current is maximum at this point. Okay, this is the first quarter and the current is maximum is at this point at the beginning of the cycle, but it becomes zero. So you can say that the current is flowing in the normal direction of the positive direction, and in the second quarter the applied voltage across the capacitor falls. So here you can see it is falling. So capacitor also discharges. Since voltage is falling, so charge will also fall. So charge is falling, which means that capacitor is being discharged in the second quarters. And current achieves the negative value. This is the negative current value because current reaches the negative quadrant in second quadrant. Okay, so when the voltage reaches zero value, it reaches the negative peak, and the third and fourth quadrant repeat itself according to this first quarter and the second quarter with the opposite polarity. Okay, so now we will see how this current is leading. So since this Q is CV, so we have applied this V is equal to Vm sin omega t, so it becomes sin omega t. Now the current is dq by dt. Okay, so when dq by dt is this, we will differentiate. So sin omega t becomes cos omega t, and cos omega t can be replaced by sine 90 plus omega t, since the sinusoidal quantity sine theta is positive in the second quadrant, and this omega c is appearing in the derivation differentiation, so it can be placed in the denominator as 1 upon omega c. So this component is replaced by this Im, and Im sine omega t plus pi by 2. So it suggests that the current is leading the applied voltage at every point by 90 degrees. Okay. So now let us focus on its power situation. So its power is VI, VMC. This is, I have just explained you. So we have this 2 sine 2 by sine 2 omega t, which is the trigonometric quantity, sinusoidal quantities, and its average will be 0. And the energy stored in the capacitor is half CV square, and half C Vm square is the maximum energy which can be stored. Okay. So this was all about the capacitive load. So since we have understood the resistive load, inductive load, and capacitive load, now the loads which are in between, which are using both these quantities, can be understood easily. Okay. So this is the RL circuit. So in this RL circuit, this is circuit diagram given. This is the phasor diagram given, which I have just explained you, that in the RL circuit, the current is lagging the voltage phasor by phi angle. Okay. Similarly, we will draw the voltage waveform, current waveform. Current will begin the its cycle or zero axis. It will be at its zero axis at phi angle. Okay, suggesting that it is lagging by phi. And again, instantaneous power is the multiplication of both these things, Vm sin omega t and Im sin omega t minus phi. So on substitution, the angle phi and time differently, we can plot the power, instantaneous power as well. Okay. So now this voltage magnitude can be understood with the help of Pythagoras theorem. This is the vector representation. So this is the hypotenuse. VR square plus VL square is equal to V square. Parallelogram of vector addition, you know everyone. Okay. So this is the angle tan inverse y upon x, you know. This is the voltage triangle, which is the representation of this. And if we remove the current from it, so it becomes the impedance triangle. R is in the base, XL is in the perpendicular, and Z is the impedance. Okay. Power factor is the cos theta or cos phi, which is R by Z. So now we will move on to instantaneous power equation. So this is the instantaneous power. So we have two sin A sin B. So we apply the formula of 2 sin A sin B as cos A minus B minus cos A plus B. So here we get one trigonometric quantity and one constant value in the instantaneous power. So when we take the average of the trigonometric quantities is 0. So it becomes 0. And we are left with this value. So this is the average value. So Vm by root 2 and Im by root 2, and it can be replaced by RMS values of sine, RMS values of current and voltage. So the power, average power becomes Vi cos phi. This formula is applicable for resistive load, capacitive load, inductive load, and the combination of any loads RL, RC, etc. So now on the same lines, we can also denote the power. So this you must have studied in your uh, labs as well. So this is our apparent power and it is given by Vi. So cos component, if we take its cos component, it becomes true power or the real power. And if we take its sine component, it becomes the reactive power. Okay. And if the current is lagging the voltage, its components are also shown here. So this I cos phi is the active or wattful or the in phase component of the current because it is in the direction of the voltage, and I sin phi is the reactive component of the current. So magnitude of the power can also be derived from the power triangle using Pythagoras theorem, and this is the power factor PF, that is R upon Z, and if we take inverse of that, it becomes the quality factor and it is denoted by Z by R. But if the magnitude of R is less, then it becomes XL by R. Okay.